Hi, and welcome to Science Says, bite-sized research that you can actually use. I'm Kirsten, the Director of Research for Carbon Sink. First and foremost, I'm a soil scientist and I love research. I read it, I write it, and I argue about it probably a bit too much. But I also know that most people don't have a lot of time or desire to dig into academic papers. So in this series, I'm going to break down some big papers and present their findings in plain English. Today's Science Says is a special one, not just because it's the first one or because I've had a couple of beers with some of the researchers in the paper, but because it shines a spotlight where it is long overdue, and that is in our dryland farming systems. Most of what we know about soil carbon comes from temperate systems, where soils are deeper, rainfall is far more generous, and the constraints to building carbon are fewer. But this new review by Chelsea Jank and colleagues pulls drylands to the centre of the conversation. And it is about time. Drylands cover like 40% of the world's surface. They have the highest population growth of all ecological zones globally, and they provide about 44% of the world's food supply. As well, they have about a third of global carbon stocks. Despite all of these things, they're underrepresented in the literature. They're definitely under a lot of pressure from climate change, and they're under increasing scrutiny as carbon markets continue to grow. So this review doesn't just ask, can we build soil organic carbon in drylands? It asks, at what cost, under what conditions, and for what gain? And I reckon that's the kind of nuance that we need. So let's dig in. Here's the big question we're tackling. What are the key levers that can actually be pulled to build soil carbon in dryland systems? This figure lays it out simply. We're dealing with two main forces. We've got inputs on the one side and losses on the other. And this is the case in all systems, whether they're dry or not. So on the input side, we've got carbon coming from plants and from animals. That means photosynthesis, roots, stubble, and if you do have livestock in the system, you've got manure as well. These are the raw materials for soil carbon, but not all inputs are created equal. Decomposing roots and rhizodeposits, those are the liquid carbon that come out through the roots and go into the soil, they tend to contribute more to long-term carbon than something like surface stubble, especially in no-till systems where that stubble could be sitting on the surface and breaking down before it even gets into the soil. But once that carbon is in the soil, it's all about what happens next. So then we get the microbes breaking down some of that organic matter. They stabilize some of it against soil particles, and then crucially, some of it gets released as CO2 to the atmosphere. That microbial process is nutrient dependent, and in drylands, it can often be limited by low fertility and patchy moisture. We also can lose carbon through erosion and leaching, and this is super important in sandy soils that have low structure. So if you kind of zoom out, building carbon in drylands comes down to two things. Maximize the carbon that's going in and minimize what's being lost. Let's talk about inputs. What you grow, how you grow it, and how often. All of these things shape how carbon enters the soil. So first up, we have our crop type. High biomass cereals can deliver more above ground residue, while deep-rooted perennials like lucerne and tropical grasses can push carbon more deeply into the soil where it's more stable. Legumes, they help to balance the carbon to nitrogen ratio and improve how microbes process organic matter. Dual-purpose crops, when they're grazed and allowed to regrow, can boost below-ground root inputs, both from the liquid carbon from the roots and how much overall root biomass is there. Then, rotation design. More diverse phases introduce functional diversity, and integrating legumes can improve nitrogen cycling and residue quality. Pasture crop rotations can offer critical windows for root recovery and for soil carbon development. Lastly, we have cropping intensity. Early sowing, reducing fallow, or intercropping, something like a cereal legume mix, can extend the growing season and increase the total biomass going into the system. But I did say this was a cost-benefit analysis, so here's the catch. Not every lever works everywhere. In drylands, pushing biomass too far can backfire on you. If a crop runs out of moisture during filling, you risk that haying off and then you've got a heap of straw and not much grain. Intercrops, they might build carbon, but if they also burn through the stored water, the main crop could suffer. The paper's key message is this: context is everything. Rainfall, soil type, nutrient constraints, and enterprise goals. These all shape whether these strategies help you or hurt you. These are the input levers, but building carbon means knowing not just what is possible in your system, but what's practical in your system and when to apply it. So we've talked about getting the carbon into the soil. Now, how do we keep it in there? So this is where your retention strategies come in. So we're slowing losses, trying to stabilize what's already there, and making sure those inputs actually become soil carbon. Your harvest strategy, first and foremost, matters. It's what's left behind and how it's going to affect those outcomes. So something like stripper fronts can leave tall stubble that breaks down slowly, which might minimally protect soil, if it's upright especially, minimally, but it limits incorporation of biomass. Destructors and low harvest heights leave a finer residue, but it's faster to break down and could be more easily lost to CO2. If you take the residue away entirely, then you're cutting carbon inputs at the source. So stubble retention helps to protect against erosion in some cases, but in no-till systems, only about 2 to 16% of that surface matter actually enters the soil. So without incorporation, it's mostly just sitting on top. And then back to no-till. That reduces erosion, but it also concentrates soil organic carbon near the surface, offering less long-term storage at depth. Some strategic tillage, if it's done right and with nutrients, can actually help incorporate residues and create the microbial conditions needed to stabilize carbon. Then, of course, you've got the livestock as well. With good management, about 40% of biomass returns as manure, and that's a really high-quality, microbe-friendly input. That grazing, as I mentioned before, can also trigger regrowth and add more root carbon to your system. But overgrazing limits that benefit. So the key isn't whether you graze or you don't graze, but it's how you manage that grazing. These retention strategies really matter, but like inputs, they only work if they're matched to your soil, rainfall, and your management goals. So you've got your carbon in the system, now what? Stabilization. It's about keeping it there long term, and that means tackling some barriers. So here we start with soil constraints. Things like acidity, compaction, salinity, and sodicity, these all limit root growth and nutrient uptake. They also restrict the depth and stability of carbon inputs. So fixing these types of things with liming, ripping, gypsum, or maybe biological solutions can open up the soil to deeper roots, better nutrient access, and stronger subsoil carbon stabilization. And that's key because subsoils with clay, for example, can actually store carbon more securely. So next, you have your erosion and your leaching. If soil isn't protected, you're going to lose what you've built. Ground cover and stubble will help, but so does good soil structure. Well-aggregated soils are less prone to wind and water erosion. So tillage might still be needed, but the timing of when that occurs is super critical. And then you've got biology, and this is where carbon is made or lost. High microbial carbon use efficiency, CUE, means that more carbon goes into the soil, into the biomass of microbes, and is less lost by CO2 to the atmosphere. Fungi can play a major role in dry, nutrient-poor soils, especially sandy soils, and they're often really good at stabilizing carbon, better than bacteria. But a little bit of caution here. Under the wrong conditions, adding too much fresh carbon can cause something that's called priming. And this is where microbes will burn through the existing organic matter in the soil to mine nutrients. And this ends up as a net loss to the system. So as you can see, it's not just about adding more biomass to the system, it's about building the right conditions for carbon to stay in the soil where we want it. So building carbon in dryland cropping, it isn't easy or risk-free. Inputs, they cost money, gains can be slow, patchy, and hard to measure, especially in dry years. And if you push too hard for biomass at the wrong time, you can lose yield. The wrong practice in the wrong time can set you back. But the benefits, they're worth it. Better water retention in sandy soils, improved nutrient cycling and a potential to reduce excess inputs, and stronger soil structure. fewer constraints, deeper roots, and most importantly, more resilience when it's dry. And we know it's getting drier. Over time, you'll get more biological activity, have less erosion, and there's also that benefit of having access to carbon markets and long-term productivity gains. This paper echoes something I often say about soil carbon. There are no silver bullets, but drylands store a third of the world's soil carbon. We cannot ignore them. With the right system, timing, and mindset, we can build soil carbon in dryland farming. And that is a future I reckon it's worth aiming for. Next time on Science Says, we're going to dive into Paige Stanley's paper and ask the question, can grazing help build soil carbon? And spoiler alert, it's not just about stocking rates. So if this helped you, give us a follow, save it, or share it to somebody who you think might benefit. Science Says is just getting started, and there's more to come.